Good morning, all of you. The second important power semiconductor device, thyristor. That was the point we were discussing about when we were in the last week, and we have covered the introduction part of thyristor, wherein we have seen what is the structure of thyristor, the symbol of thyristor, then which three terminals are there for thyristor, and how it looks. That is what is the physical appearance of a thyristor, and then different manufacturing techniques of thyristor. That part we have covered in the last session. Today we are going to discuss the characteristics of thyristor. As we all know that every power semiconductor device is characterized with the help of few parameters in thyristors or those devices. Now, which thyristor or which characteristics thyristor does have? We have to study VI characteristics of thyristor, then switching characteristics, and then gate characteristics of thyristor. So most of the semiconductor devices are known for their characteristic, are known for their nature of characteristic, and could be well understood, studied the principal operation of thyristor or any semiconductor device with the help of those characteristics, and that's why those are very important. Okay. Before we proceed further, I would like to take a review of what we discussed in the last session. As I mentioned, we have seen the structure of thyristor. Now we know that the thyristor is configured of four different semiconductor, four layers of semiconducting material of P, N, P, N. That is, there are four layers which are alternately placed. We know that there are two types of semiconducting material, P and N. So P type, then it is N type, then it is P, and then it is N. So there are four layers. So naturally, they'll form three junctions among them. So you may refer the junction between P and N to be J1, then junction between N and P to be J2, and junction between P and N again, this is J3. So we have three different junctions, four different layers, and three different terminals. Now the terminal which is to the P side of the thyristor, because since there are four layers, one of the side is of P material and another side will be of N material. So P side terminal, we always connect it to the positive terminal of the supply, positive terminal of the bias. We call it as a forward bias. So when it is in the forward bias, then P side terminal, this terminal is called as anode. Okay, and the opposite terminal of anode is always cathode. What remains and what extra with the devices like thyristor, which are supposed to be half controlled or full controlled like that, we have extra terminal called gate. I'll mark it with a star because this is very important, gate. Because normally when we see diode or power diode, we know there are two terminals, anode and cathode. What extra thyristor have? That is gate, this extra terminal. Now where this gate is available, gate is connected to that P side or that P layer of thyristor which is close to the cathode. So naturally the first P layer will have anode and the latter P material or P layer will have gate. Okay, and rest the cathode is connected to the N side. Okay, so this is how the terminals are available for thyristor. Now what I am trying to emphasize here is you cannot connect any terminal anywhere. For example, if I say I will connect cathode here at N terminal, okay, because let it be N. So whichever is the layer, what happens? Means what is the difference? Actually, there is a difference. Okay, so we must connect cathode to the opposite of anode. Means the extreme bottom to the extreme bottom layer of the thyristor. So this has to be cathode, and gate should be connected to that P layer which is close to the cathode. So this is how we should draw the structure of thyristor. Now based on this structure, if you look at it parallelly, I have drawn the symbol of the thyristor. So thyristor parallel, it will have anode, and this will be cathode, and this will be gate. Now you can observe gate is close to the cathode. Okay, so symbol can be drawn like this. So if you remove gate terminal from here, it will look like it is diode, power diode. But since it is provided with extra feature or extra terminal, that is gate, we need to show the gate here. Okay, so this is how we should understand the structure of thyristor and its symbol. Okay, and importantly, we must know there are three junctions, J1, J2 and J3, and based on the working of these three junctions, or based on the nature of these three junctions, we will define the operating modes for thyristor. So I guess this also has been covered in the last lecture. Based on how we connect thyristor in a power circuit, we devise three different operating modes for thyristor. The first operating mode we call it as a reverse blocking mode. Reverse blocking mode, where the diode is the thyristor is connected in the reverse bias. Okay, so very small reverse leakage current flows through the thyristor. So we may assume the device to be open circuit, okay, and it is in the off state. So which terminologies are related with the reverse blocking mode of thyristor where it is in the operation? We should connect thyristor in the reverse bias. So how we connect thyristor in the reverse bias? We should connect anode to the negative terminal of the bias, okay, and cathode to the positive terminal of the bias. Okay, this is how we connect the thyristor in the reverse bias, provided in this mode gate has nothing to do. So gate is not connected yet. So gate has no role in this mode, reverse bias. There is no role for gate. Okay, it has yet to play its role. Okay, so in the first mode of operation, reverse blocking, we are keeping gate terminal open. Accordingly, we are connecting anode to the negative terminal and cathode to the positive terminal. Hence, we call it as a reverse bias. And in this mode, what happens? The very small leakage current flows due to the minority carries only. Okay, and that current we call it as a reverse leakage current. Getting it? So that reverse leakage current is very small. Okay, very small. And in this mode, what happens? In this mode, very importantly, because as I said, because of junction J1, J2, J3 and their nature of operation, we could get this modes. So in the reverse bias mode, what happens? Since anode is connected to the negative terminal and cathode is connected to the positive terminal, that is in the reverse bias, junction J1 is reverse bias, junction J3 is reverse bias, and only junction J2 is forward bias. So you may also specify like junction J1, it is in the reverse bias, junction J2, it is in the forward bias, and junction J3, it is in the reverse bias. So we have two We have two junctions, J1 and J3. These two junctions are reverse bias. And the only junction which is forward bias is junction J2. So the cumulative current is only reverse current because two junctions are reverse bias, only one junction is forward bias. So cumulative current is reverse current, so that current is very less as well, and because of that this current is called as reverse leakage current. Okay, in the reverse blocking mode. So more importantly, this is not only reverse bias but this is reverse blocking. It will block the voltage, it will block the reverse current. It will allow the reverse current very small, which is very small in magnitude, but it will block the reverse voltage. That voltage we call it we call it as a reverse blocking voltage. Okay, reverse blocking voltage. So that voltage value magnitude is very high. Actually, very less leakage current we get, but very high voltage is blocked, reverse voltage is blocked. Okay, and that too negative voltage, remember, because this is in the reverse bias, the thyristor is in the reverse bias. Okay, so this is how the first mode works for thyristor. Now the second mode is again blocking, but now it is forward blocking. Now in this mode what happens? The diode is connected in the forward bias. Sorry, the thyristor is connected in the forward bias. Thyristor is forward bias means anode is connected to the positive and cathode is connected to the negative. This is how we normally connect the given semiconductor device. So now this is in the forward bias thyristor. Now because of that, what happens with the junctions? Because of that, what happens with the junctions? With this, junction J1 is in the forward bias, junction J2 is in the reverse bias, and junction J3 again it is in the forward bias. Okay, that junction J1 and J3 they are in the forward bias. Junction J2 is still in the reverse bias, but still there is opposition. So the current now which is from anode to cathode, this current is now forward current. But still that current experiences a very high impedance. High impedance. This is very important terminology. High impedance. It experiences very high impedance, because of it, which its magnitude is very less, even though the current flows, the forward current flows. Forward current we get. Forward current, that is the current from anode to cathode. We get, but this is very less, very small current. Hence, this current is called as forward leakage current. Forward leakage. This is forward leakage current. The current is in the forward direction. We get expected current. Expected current in the sense current must be from anode to cathode. That is our expectation. But still, the value of that current is very less because of the presence of junction J2, which is in the reverse bias, which imposes very high impedance to the forward current through the device. Now the current flows from anode to cathode means through the device. So when it is flowing through the device, it will experience very high impedance, because of which its value will be very less. Its magnitude will be very less. But though the current flows in the forward direction, it is small. Hence, that current is called as forward leakage current. Earlier we had reverse leakage current. Now we have forward leakage current. Are you getting? So forward leakage current and reverse leakage current. We get reverse bias, reverse blocking mode, and in the forward blocking mode. And the third mode is very important. Third mode is very important. That third mode is forward conduction. Now we get the expected operation of the device. Now here in this case, in the first mode, we call device to be open circuited, means off state. In the second mode as well, the device is said to be open circuited as if it is off state, though it is very small current flows. We say it is open circuited and in the off state. Okay. So in both these modes, we say the device is in the off state. Now, in third mode, we connect gate terminal. In earlier two modes, there is no role of gate. Gate has no role to play in first mode and in the second mode. That is reverse blocking and forward blocking. Gate is not connected. But in the third mode, where the thyristor is in the forward bias, okay, normally very similar to the forward blocking mode. But what is added feature with the forward conduction or extra what we are doing here is we are connecting gate, and that too we are applying positive voltage to the gate terminal and we are connecting it along with the cathode. Means what? The gate is provided with the positive spike or the pulse, for example, or positive potential we are providing to the gate, and as compared to cathode it will be at higher potential. Now because of that, what happens, gate penetrates some electrons in the layer which is connected to the gate terminal. So we get here the electrons. In this layer we get electrons. Okay. Now the above layer, this N layer, and below this, both the layers, they are N type of layer. Okay. And in between them there is a P type of layer to which gate is connected. But when the gate is provided with the positive potential, there is a current. There is a current from gate to P material or P layer, because of which there is exchange of polarities or exchange of carriers. So how they will exchange? Gate will give some electrons or insert some electrons in this layer, because of which what happens, to the both side of this layer there are electrons. So what happens with that? Junction will get vanish. This junction J2 will get vanished. So when we connect in the third node, when we connect thyristor, it is already in the forward bias, because of which junction J1 is in the forward bias, junction J2 earlier it is reverse bias, and junction J3 it is in the forward bias. It is very much similar to the second mode. But what happens after some time, since gate is connected, gate will make this junction J2 to eliminate or disappear. So there is no impedance from this junction J2 to the flow of current. There is no opposition, because it will get vanished. This J2 will get vanished because of gate terminal which is connected now. So gate is playing an important role at the time of the operation of thyristor. When it is made on, during on operation, gate is playing its role. How it will play? It will vanish. It will make that junction J2 to vanish, because of which there is no reverse bias junction available. Only two junctions now present as if that is junction J1 and J3, but both of them that are forward bias, because of which we will get expected forward current, because of which we may say the switch or the device is in the on state or it is closed. अगोदरच्या दोन मोड मध्ये, रिव्हर्स ब्लॉकिंग आणि फॉरवर्ड ब्लॉकिंग मध्ये, थायरिस्टर हा ओपन सर्किट होता. आता काय झालं, तो क्लोज होता, आणि त्याच्यामुळे थर्ड जो मोड आहे त्या मोड मध्ये तो डिव्हाइस थायरिस्टर हा ऑन आहे असं आपण म्हणू शकतो. ठीक आहे. हे कशामुळे झालं? गेट पिक्चर मध्ये आल्यामुळे, गेट ऑपरेशन मध्ये त्याने पार्टिसिपेट केल्यामुळे कसं झालं की त्याने काय केलं, इलेक्ट्रॉन्स काय केलंय, इन्सर्ट केलंय पी लेअर मध्ये. आता पी लेअर ऑलरेडी होल्स असतात, परंतु त्याच्यामध्ये जर जास्त इलेक्ट्रॉन्सची डेन्सिटी झाली तर काय, तो पी राहणार नाही, तो एनच होणार. मग त्याच्या वरती पण एन आणि खाली पण एन, म्हणजे काय, तिथं कुठलंही जंक्शन नसणार आहे. दोन एन मटेरियल जर आपण एकत्र जोडले तर तिथं जंक्शन आहे असं म्हणू शकतो का आपण? नाही म्हणू शकत. ओके, म्हणजे या बाजूला इकडे अगोदर पी होता, परंतु त्याच्यामध्ये इलेक्ट्रॉन्सच जास्त झाले. कशामुळे? गेटच्या कंडक्शनमुळे. इलेक्ट्रॉन्स जर जास्त झाले तर इथं काय होणार आहे, तो एन मध्ये कन्वर्ट होईल, ऍज इफ नॅचरली तो पीच आहे, परंतु त्याच्यामध्ये इलेक्ट्रॉन्स जास्त झाले, डेन्सिटी वाढली इलेक्ट्रॉनची. त्यामुळं अगोदरचे इलेक्ट्रॉन्स जे वरच्या लेअर मध्ये होते त्यांच्यामध्ये जे जंक्शन होतं त्याच्यामुळं ते जंक्शन काय झालं, निघून गेलं, इलिमिनेट झालं, वॅनिश झालं. जंक्शन J2 जर जात असेल निघून, तर राहिले कुठले, J1 आणि J3, which are already formed by us, because of which we get considerable current or expected forward current. ओके, याला फॉरवर्ड करंटच म्हणायचं. एक्सपेक्टेड मी म्हणतोय कारण आपल्याला एक्सपेक्टेड व्हॅल्यू मिळते करंटची, जी लिकेज करंट पेक्षा कितीतरी जास्त असते. ओके, सो व्हाय these three modes are important at the time of characteristic of power diode, characteristic of thyristor. We take help of these modes. Actually these modes will result in the characteristics of thyristor. Okay, these modes will help you to draw the VI characteristics of thyristor. Okay, so because each mode will result in different region in the characteristic. प्रत्येक कॅरेक्टरिस्टिकला रिजन असतात, यातला प्रत्येक मोड हा एक रिजन रिप्रेझेंट करतो. आता नॅचरली किंवा बाय ऑब्झर्वेशन यू कॅन से that there are three regions because there are three blocking modes. म्हणजे प्रत्येक मोड हा एक रिजन रिप्रेझेंट करतो. म्हणजे जर मोड 3 असतील तर रिजन किती असणार आहेत, कॅरेक्टरिस्टिकला 3 असणार आहेत. ते कुठले आणि कुठे येतात आणि कसे येतात, दॅट वी विल डिस्कस in the VI characteristics of thyristor. Okay, so I will intro with you the VI characteristic of thyristor or SCR. Remember, thyristor is a family, SCR is a device which has 90%, more than 90% similar characteristic which thyristor should have. ओके, म्हणजे एससीआर ला अल्टरनेटली थायरिस्टर म्हटलं जातं. याचं कारण असं आहे की एससीआर मध्ये थायरिस्टर साठी जे एक्सपेक्टेड कॅरेक्टरिस्टिक किंवा एक्सपेक्टेड फीचर्स आहेत ते 90% पेक्षा जास्त आहेत. म्हणजे थायरिस्टर म्हणजेच एससीआर असं आहे. परंतु थायरिस्टर ही फॅमिली आहे, त्याच्यामध्ये अजून पण मेंबर्स आहेत, बट एससीआर इज व्हेरी क्लोज टू दी थायरिस्टर. ओके, दॅट्स वाय we can call SCR alternately as a thyristor. Okay, so VI characteristic of thyristor. So it will look like VI characteristic. As I told you, there are three types of characteristic: VI, then we have switching characteristics, and the third characteristics are gate characteristics. Gate characteristics. So we will discuss VI characteristics. In case of VI characteristic, the voltage is always founded on x-axis and current is on y-axis. So this pipe is for gate current 1, this for gate current 2, and this for gate current 3. Okay. This is IG1, IG2, and IG3. So mark this as a here IH, which is holding current, and this point, this as a IL, which is latching current. I will discuss, I will explain it to you what is holding current, what is latching current. So these two terms are very important. Then this particular voltage, we call it as a VFBO, means forward breaker voltage. And this voltage, this particular is VRBO, that is reverse breaker voltage. Okay, we know we get the reverse current in the third quadrant. So this is reverse leakage current. Reverse leakage current. Okay, and this is this current, this part here up to this we get forward leakage current. Forward leakage, and this is actually forward current, which is expected. You can look at this. The magnitude of this current is very high. Means this is actual characteristic. Actual characteristic. When the thyristor is actually turned on, when it is in the operation. So this is forward current. Forward current. Okay. So initially we get reverse breaker voltage, reverse leakage current.
Hello, sir.
Forward leakage current, forward current. Okay, and forward breaker voltage. Okay, now we have this holding current and latching current. What these terminologies are. Before that, as I told you, or as I mentioned, we have three different modes for thyristor and its operation. That is forward blocking, reverse blocking, then forward blocking, and forward conduction. This part in the third quadrant, where we get reverse leakage current and the voltage we call it as a reverse breaker voltage. This region, this particular region of operation, this one, this region of operation is nothing but reverse blocking region. Reverse blocking. Okay. This region in the first quadrant, which I am shading now, this is forward leakage. Forward blocking region. Forward blocking region. Okay. And above this, where we get forward current normally when the device is in the operation, when it is in the on state, this region, this one, this region, we call it as a forward conduction region. Forward conduction region. That is, it is clear that each mode of operation of thyristor results in a particular region. Means if there are three modes, we get three different regions across the VI characteristics of thyristor. Okay, म्हणजे thyristorला आपल्याला तीन मोड आहेत आपण म्हणतो, रिव्हर्स ब्लॉकिंग, फॉरवर्ड ब्लॉकिंग आणि फॉरवर्ड कंडक्शन. हे तिन्ही मोड तीन वेगवेगळ्या रिजन मध्ये ऑपरेट होतात. आणि त्याच्यामुळे आपल्याला VI कॅरेक्टरिस्टिक हे 3 वेगवेगळ्या रिजन मध्ये मिळतात. त्या 3 रिजन्सना काय नाव आहे? रिव्हर्स ब्लॉकिंग, त्यानंतर फॉरवर्ड ब्लॉकिंग आणि त्यानंतर फॉरवर्ड कंडक्शन. मीन्स इवन their titles are very similar to that of the modes of thyristors. Okay, so for these VI characteristics, what is very important is how to connect the device. So normally the device is connected like, we have thyristor like this. This is gate, this is cathode. So again, cathode should be provided with the circuit with gate like this. So this is cathode and this is anode. So this is how we should connect, or we should draw the circuit for VI characteristics of power diode. Okay, now this is positive terminal and negative terminal for anode and cathode. So this happens to be anode, this is cathode, and this is gate. So we have connected gate in the circuit. We have connected thyristor in a such a way that it is in the forward bias, and because of which we get these characteristics. Now, what is important is this is forward current. We call it as a IF, forward current. That is current through the device from anode to cathode. This is forward current. This current is gate current, IG. And say here IG1, IG2, IG3. So which parameter we are changing? We are changing gate current by changing this voltage, by which we get the forward current at a particular value of this gate currents. Okay, and again we are applying what? The voltage. So this is voltage. Now if this voltage is negative, means this is in the reverse bias, so we get reverse breaker voltage at a particular time or instant, because of which there is a breakdown of junctions. As we studied, there is a breakdown of junctions and we get very high current. Okay, then when it is positive voltage, we get forward breaker voltage. At some particular voltage, the junction J2 will disappear and it will start to conduct a very high current from anode to cathode, or expected current from anode to cathode. That particular voltage we call as a forward breaker voltage. The voltage at which junction J2 disappears. Okay, that is forward breaker voltage. The voltage at which, the reverse voltage at which junction J2 breaks down, J1 and J3 break down, that voltage we call it as a reverse breaker voltage. Okay, so if we go on increasing the voltage and changing the current, what happens? Suppose now the thyristor is in the forward bias, anode to cathode, we have connected forward bias, and we are applying different gate current value or different gate current to the device, gate terminal. So as we go on increasing the forward voltage, at a particular voltage, the junction J2 will get disappear and the forward current will start to conduct. Okay, the forward current will start to conduct. That is, it is about to enter in the conduction mode. The minimum value of the forward current at which the device said to be, it is conducting current in the forward direction. That value of the current we call it as a latching current. It is the minimum value of the forward current at which device starts to conduct. म्हणजे फॉरवर्ड करंटची अशी कमीत कमी व्हॅल्यू की ज्या व्हॅल्यूच्या पुढे आपण असं म्हणू शकतो की डिव्हाइस कंडक्ट व्हायला सुरुवात झाली. दॅट मिनिमम व्हॅल्यू ऑफ द डिव्हाइस वी कॉल इट एज अ लॅचिंग करंट. That is, device is latched into the conduction. Latched, just like entering into the conduction. So latching means device will start to conduct. Okay, so that minimum value for which the device conducts is called as latching current, and this minimum value belongs to forward current. So you may define latching current to be that minimum value of forward current at which device is about to conduct or device will start to conduct. This value is latching current. Okay. So the first term is clear, latching current. अशी कमीत कमी फॉरवर्ड करंटची व्हॅल्यू की ज्या करंटच्या पुढे डिव्हाइस कंडक्शन मध्ये आला असं आपण म्हणू शकतो ती व्हॅल्यू म्हणजे लॅचिंग करंट. ही कशाची व्हॅल्यू आहे? फॉरवर्ड करंटची व्हॅल्यू आहे, कमीत कमी व्हॅल्यू. ओके. त्याच्यानंतर समजा आपल्याला करंट कमी करायचं आहे, फॉरवर्ड करंट आता आपल्याला एक्सपेक्टेड काय मिळते, ऑपरेशन मिळते. आता आपल्याला डिव्हाइसला ऑफ करायचं समजा, त्या केसमध्ये आपण काय करणार आहे, हे जे फॉरवर्ड व्होल्टेज आपण अप्लाय केलं होतं ते कमी कमी करत आणणार आहे, शिवाय गेटची जी व्हॅल्यू आहे ती सुद्धा कमी करत आणणार आहे असं आपण म्हणू. सो इन दॅट केस व्हॉट हॅपन्स, द फॉरवर्ड करंट विल स्टार्ट टू डिके. डिके मीन्स डिक्रीज, and it will go on decreasing at some particular voltage. At some particular voltage device will stop to conduct. So it is the minimum value of the forward current for which, before which device is in the conduction, or it is the minimum value of the forward current. Okay, minimum value of the forward current before device stops to conduct. So holding current and latching current, these two terms are associated with the forward current. Latching current is the minimum value where device is about to conduct, and holding current is the minimum value of the current when device is about to stop from the conduction. Okay, that is the vice versa. But normally what happens if we compare latching current and holding current of the same device, because these two terms are associated with the switching of the thyristor. One current indicates turn on, another current indicates turn off. Latching is during turn on and holding is during turn off. So if we suppose that, okay, if we assume that, and if we compare latching current and holding current, or in any condition, latching current is always greater than the holding current. So holding current is minimum. So if we say latching current has like 0.5 milliampere, okay, then holding current is like 0.3 milliampere or 0.2 milliampere, like that. So if we compare for the same device, latching current and holding current, latching current is always greater than the holding current, or vice versa, holding current is always less than the latching. This relation is very important. म्हणजे कोणत्याही थायरिस्टर साठी लॅचिंग करंट हा होल्डिंग करंट पेक्षा मोठा असतो. जरी तो खूप 1 मिलिअम्पियर किंवा 2 मिलिअम्पियरचा फरक असेल तरी सुद्धा इफ यू कंपेअर ऑलवेज लॅचिंग करंट इज हायर दॅन द होल्डिंग करंट. ओके, so this is how we should learn the characteristics of VI characteristics of thyristor. Okay, now as I mentioned, these characteristics are resultant of the mode of operation of the thyristor, okay, which are giving us the three different regions: reverse blocking, forward blocking, and forward conduction, in which we get different terms associated with it. Okay, now in reverse blocking, which are the terms important? The first important term is reverse breakover voltage. The next important term is reverse leakage current. Okay, so these two terms are important. So in this region, you may say device is in the off state, as if it is in the off state, or it is open circuit, like that. Okay, imagine. So you can conclude from the understanding what you understood from here. Okay, in the forward blocking region, which are the terms associated? Forward leakage current and forward breakover voltage. Okay, now in the forward conduction, which are the terms associated? Forward current, okay, latching current and holding current. Out of which latching current and holding current, their relation and their terms. What do you mean by latching? What do you mean by holding? That is very important. Okay. And if we go on changing the gate current, for different gate currents we get different value for breaker voltage. म्हणजे समजा IG1 ला ब्रेकर व्होल्टेज इथं आहे, तर IG2 ला ते इथे येणार आहे, IG3 ला ते इथे. ओके. ऍक्च्युली हा जो IG3 असतो, आता IG1, IG2, IG3 यांच्यामध्ये रिलेशन दाखवतो. IG3 हा सगळ्यात मोठा असतो, त्याच्यानंतर IG2, त्याच्यानंतर IG1. असं काय नाही की तीनच गेट करंट असायला पाहिजे, एकापेक्षा जास्त असू शकतात. किंवा याच्यावरून आपण काय कंट्रोल करू शकतो, मुव्हिंग फ्रॉम राईट टू लेफ्ट, द व्हॅल्यू ऑफ गेट करंट गोज ऑन इन्क्रीजिंग, वेअर द व्हॅल्यू ऑफ ब्रेकर व्होल्टेज गोज ऑन डिक्रीजिंग. ओके. म्हणजे जितकं ब्रेकर व्होल्टेज जास्त तितकं गेट करंट कमी लागतं, जितका ब्रेकर व्होल्टेज कमी तितका गेट करंट जास्त लागतं. आर यू गेटिंग दिस? म्हणजे लेफ्ट कडून राईट कडे जाताना ब्रेकर व्होल्टेज वाढतंय, परंतु गेट करंट काय होतं, कमी कमी होत जातं. हे बघायचं इथं पण दिसतं. ओके. सो दॅट इज हाऊ the relation between breaker voltage and gate current, or the relation among the different values of gate current for the same device. Okay. This also may be asked, what happens with the gate current if we go on increasing the breaker voltage? It will decrease. Okay. What happens with the gate current if we go on decreasing the breaker voltage? It will increase. Like that. Or what is the relation between latching current and holding current? Are they equal? If latching current is greater than or less than the holding current, like that. This must be remembered. Okay. And how to connect the thyristor to draw the VI characteristic is like this. So you may call this as a circuit for VI characteristic. म्हणजे जसं आपण डायोडची कॅरेक्टरिस्टिक ड्रॉ करण्यासाठी त्याचं सर्किट अगोदर ड्रॉ करतो, त्या पद्धतीनं तुम्हाला हे पॉवर सर्किट आहे ते ड्रॉ करावं लागेल, त्याच्यावरून तुम्हाला हे एक्सप्लेन करायचं. म्हणजे हे लक्षात आलं पाहिजे की कुठला पॅरामीटर कुठं मेजर करायचं. फॉर एक्झाम्पल मी म्हणेन फॉरवर्ड करंट, परंतु फॉरवर्ड करंट इथं कुठे आहे, जो करंट एनोड कडून कॅथोड कडे जातोय या डिव्हाइसच्या स्ट्रक्चर मधून किंवा बॉडी मधून, तो आहे फॉरवर्ड करंट. तर ब्रेकर व्होल्टेज म्हणतोय आपण, तर ते ब्रेकर व्होल्टेज कुठे आहे, तर एनोड आणि कॅथोडच्या मधलं व्होल्टेज म्हणजे ब्रेकर व्होल्टेज. गेट करंट म्हणतोय आपण, गेट करंट कुठे आहे, जो करंट गेट मधून डिव्हाइस मध्ये एंटर करतोय तो आहे गेट करंट. गेट कुठे जोडतात नेहमी, गेट हा कॅथोड सोबत जोडतात, एनोड सोबत गेट तुम्ही जोडू शकत नाही. ओके. सो दीज थिंग्स यू मस्ट ऑल्सो बी कीप इन माइंड. ओके. सो this is what VI characteristics of our VI characteristics of SCR or thyristor. Okay. So I'll stop the video and I'll just share the screen, so you'll get it more clear. I'll explain it in 10 minutes. You have to be there. So silicon control rectifier is characterized by three characteristics: VI characteristic, which are static characteristics, okay, switching characteristic, dynamic characteristic. They are also termed as a dynamic characteristic. So if anybody asks you, or for example, in a gate or in MCQ type of exams, where they mention instead of VI characteristic, if they mention static characteristics of SCR, it means VI characteristic. And if they ask dynamic characteristic, if they say like dynamic characteristics of SCR, dynamic characteristics are nothing but the switching characteristic. Okay? And the third type of characteristics are gate characteristic. So first type of characteristic we have seen today. Second and third will be discussed in the upcoming sessions. So VI characteristic of SCR result of modes of conduction of SCR. मी जे तुम्हाला सांगितलं की VI कॅरेक्टरिस्टिक आपल्याला मिळतात कुठून. VI कॅरेक्टरिस्टिक आपल्याला थायरिस्टरच्या मोड्स ऑफ ऑपरेशन मधून मिळतात SCR. It reveals that the SCR has three basic modes of operation: reverse blocking, forward blocking, and forward conduction. Okay, these are the three modes of operation that we have seen earlier. Now this is how VI characteristic circuit can be drawn. मी जे सर्किट ड्रॉ केलेलं आहे ते सिंपल आहे. इथं आपल्याला व्हेरिएबल व्होल्टेज अप्लाय करायचं आहे एनोड टू कॅथोड मध्ये. त्यामुळे त्या ठिकाणी काय टाकलेलं आहे, व्हेरिएबल रेजिस्टर टाकलेलं जोडलेलं आहे. ठीक आहे. तर तुमच्या हे इथं लक्षात यायला पाहिजे की फक्त व्हेरिएबल व्होल्टेज आपल्याला जसं मी म्हटलं की ज्यावेळेस एक्सपेक्टेड करंट मिळाल्यानंतर आपण काय करतो, करंटची व्हॅल्यू कमी करण्यासाठी ब्रेकवर व्होल्टेज कमी करतो किंवा फॉरवर्ड जे व्होल्टेज आपण अप्लाय केले एनोड आणि कॅथोडच्या मध्ये ते कमी करायचं आपल्याला. तर त्या केसमध्ये काय केलं जातं, तर रेजिस्टन्स बदलला जातो इनपुटचा. ओके, सोर्स साईडचा रेजिस्टन्स जर तुम्ही बदलला तर व्होल्टेज बदलतं. सो त्याच्यासाठी हे सर्किट ड्रॉ केलं आणि या कॅरेक्टरिस्टिक्स. आता बघा, सुरुवात करायची आपण रिव्हर्स ब्लॉकिंग पासून. रिव्हर्स ब्लॉकिंग आपल्याला कधी मिळतं, रिव्हर्स ब्लॉकिंग रिजन हा आपल्याला रिव्हर्स ब्लॉकिंग मोड मध्ये मिळतो, ज्याच्याशी व्हीबीआर म्हणजे काय, ब्रेकवर व्होल्टेज, रिव्हर्स ब्रेकवर व्होल्टेज. मी त्याला फॉरवर्ड आणि रिव्हर्स असं म्हटलेलं आहे. तुम्ही व्हीबीआर किंवा व्हीबीओ असंही म्हणू शकता. ओके, तर व्हीबीआर म्हणजे काय, रिव्हर्स ब्रेकवर व्होल्टेज. आणि या व्होल्टेजच्या अगोदर जो आपल्याला करंट मिळतो तो आहे लिकेज करंट, जो ग्रीन कलरने इथं दाखवलेला आहे तो लिकेज करंट. आणि या रिजन मध्ये काय केलं जातं, व्होल्टेज ब्लॉक केलं जातं, म्हणून त्याचं नाव ब्लॉकिंग म्हटलं जातं. व्हॉट ब्लॉक्स, द व्होल्टेज इज ब्लॉक्ड. व्हॉट इज ब्लॉक, द व्होल्टेज इज ब्लॉक्ड. ओके, सो रिव्हर्स व्होल्टेज इज ब्लॉक्ड, सो इट इज the reverse blocking mode. But after that voltage, that value of the voltage, which VBR, that is reverse breaker voltage, we experience very huge current through the device in the reverse direction. Because of which junction J1, J2, J3, they will get breaks down. There is avalanche breakdown. We call it as a avalanche breakdown. This is another term associated with the characteristic. Avalanche breakdown takes place when very heavy voltage is applied across the thyristor in the reverse direction, because of which junctions will get breakdown, and that breakdown is such that if junction J2 breaks, J1, J3 breaks, they will also break the J2. So like that. So that is avalanche breakdown. Okay, cumulative operation, because of which very high current we get. And the next region is forward blocking region, where the forward voltage is also blocked up to particular voltage. Okay, up to particular voltage. So we have IG, IG1, IG2. मी इथे IG1, IG2, IG3 अशी ना दिलेले आहे. यांनी IG, IG1, IG2 असं घेतलेलं आहे. परंतु त्यांचं रिलेशन बघा, IG2 सगळ्यात मोठा आहे, IG1 IG2 पेक्षा लहान आहे आणि IG हा सगळ्यात लहान आहे. म्हणजे काय, ब्रेकवर व्होल्टेज जसं वाढत जाईल तसं गेट करंट हा कमी होत जातो. ओके, त्याच्यानंतर फॉरवर्ड कंडक्शन मध्ये जातो आपण. फॉरवर्ड कंडक्शन मध्ये आपल्याला एक्सपेक्टेड करंट भेटतो, कन्सिडरेबल करंट भेटतो फॉरवर्ड करंट एनोड टू कॅथोड. परंतु हा करंट भेटत असताना एक टर्म इम्पॉर्टंट आहे ती म्हणजे लॅचिंग करंट. द मिनिमम व्हॅल्यू ऑफ द फॉरवर्ड करंट after which the device starts to conduct is latching current. Okay, and after that if we decrease the voltage, so current will start to decrease. So when it decreases, uh, the minimum value of current after which device is supposed to be in off state, that value is holding current. And the relation between latching current and holding current is latching current is always greater than the holding current. That also can be seen through the characteristics. Okay. So which are the terms associated with the forward conduction? Latching current, holding current, and forward current. Okay. So again, same plane VI characteristics of SCR can be divided in three operating regions: region of reverse blocking, region of forward blocking, region of forward conduction. Okay. Now, in the region of reverse blocking, which are the terms associated? Reverse leakage current, reverse breaker voltage, and avalanche breakdown. जसं मी तुम्हाला सांगितलं की avalanche breakdown म्हणजे काय? जंक्शन जे आहेत, 3 जंक्शन J1, J2, J3 ते ब्रेक होतात आणि त्याच्यामुळे रिव्हर्स करंट एवढा हेवी फ्लो होतो की त्याची व्हॅल्यू खूप वाढते. आणि हे कशामुळे होतं की जंक्शन्स एकमेकांना ब्रेक करतात. ते जे ब्रेकडाऊन आहे त्याला avalanche breakdown असं म्हणतात. Okay, so in that region we get reverse leakage current, reverse breaker voltage, and avalanche breakdown. So look at it how the device is operated like. It is in the reverse bias. Okay, region of forward blocking. Now in earlier case also in reverse blocking or in the forward blocking, gate is not connected. Okay, only anode and cathode they are playing their role. So forward bias thyristor is connected, then forward breaker voltage is applied, then device is supposed to be in open switch, and it is in the off state because junction J2 is still in the reverse bias. Even though junction J1 and J3 they are forward bias, the current will experience very high impedance. So we may not get considerable current in this region, and voltage is blocked, and that voltage is positive voltage, that voltage is forward voltage, hence it is called as forward breaker voltage. Okay, so these are the terms associated with the second region of forward blocking. Now the region of forward conduction, the expected operation of any device. So following terminologies are associated: latching current and holding current. So it defined as the minimum value of the anode current which it must attain during the turn on process to maintain the conduction when it gate signal is removed. Okay, even though gate is removed after latching current, device will start to conduct. Okay, so I will explain that how gate or why gate is to be removed. I will explain in the next session. And holding current, it is defined as the minimum value of the anode current below which the SCR gets turned off. म्हणजे त्याच्यानंतर काय होतं, होल्डिंग करंट नंतर SCR हा ॲज इफ टर्न ऑफ झालेला असतो. लॅचिंग करंट इज मोर दॅन दी होल्डिंग करंट. लॅचिंग करंट इज असोसिएटेड विथ द टर्न ऑन प्रोसेस and holding current is associated with the turn off process. Okay, so in this region the SCR behaves as if it is closed switch, that is on state. Okay, now device is in the on state. Okay, so region of forward conduction. Look at how gate is connected. Gate is connected between gate terminal and cathode. Okay, and gate is always provided with the positive pulse. So that's it. Four 401.
Present, sir.
2.
Present, sir.
3.
Present, sir.
4.
Present, sir.
5,
Present, sir.
6,
Present, sir.
7, 407, 408,
Present.
409,
Present, sir.
10, 10, 11,
Present, sir.
12,
Present, sir.
13,
Present.
14,
Present.
15,
Present, sir.
16,
Present, sir.
17,
Present, sir.
18,
Present, sir.
19,
Present, sir.
20,
Present, sir.
21,
Present.
22,